everybody. So another quick one. I got asked, okay, so how does SPI work when you're not bit banging? So I figured I would show you. First things first, connections. AVR has on it on port. This one particular that I'm using is 1284 on port B. We've got some UART stuff here. So we've got not SS, slave select, Mosby MISO, and SCLOC. So I'm looking at 44.123. So it's port B4, 5, 6, and 7. Although we're not using MISO because we're not we're doing we're master mode, so we're not getting any data. We're transmitting data. So I'm pretty much using 44, 1, and 3. So if I wanted to send a packet to a PLL, this is essentially what we're going to do. So here's our connections. Now, the datasheet covers SPI fairly easily. What's nice is the fact that you can, do LSB or MSB, by toggling, a register. So it's fairly easy. You don't have to do any of your own bit flipping. It'll do it for you. Stuff like that. You basically just set up the microcontroller and let it transmit everything for you. So the datasheet has all that you pretty much need to do it. We've got example code even in here for assembly, or if C is your thing. Again, more assembly, more C if you're doing slave. To transmit, I mean, this is it. I mean, it's not a whole lot to transmit SPI. So this is why, if you have the hardware, you would just use the hardware because it will do everything for you. So of course we've got all this wonderful stuff, and we've got our phase and all that kind of stuff for the various registers. Perfect documentation on this. What's going on with the registers. So this is what we've got here. So first we're gonna set the data direction on our pins as outputs. For 7, see, it's DDB7, DDB6, DDB5, and so on and so forth, which corresponds to these. The B4, B5, B6, B7. So it's, port B4, 5, 6, 7. Just setting these four as outputs. When we come to SPCR, SPCR is another register, which is what we've got here. So if we look at what we're setting, okay, so SPIE is an interrupt, and you can see here I'm setting that to 0. We're not using any interrupts, so we're not going to enable it. Data ordering is a 0. I don't have these in order. I just sort of type them as I think about them. Data, so it's bit 5. We're just doing our shifting here. When it's set to 1, LSB. When it's set to 0, it's MSB, because we have to transmit MSB in this. So that's the order. We've got the phase, master slave select. This is an important one. So we've got MSTR. As you see, I'm setting a 1 in that register. We got the polarity, which is going to be a 1. So we've got phase. So we want that phase to be on a falling edge for this particular thing. And clock rate select, SPR 0. So we're setting a 1 in 0. So we're just frequency divided by 16. So this is clocked at 8 megahertz. So it's basically 8 megahertz divided by 16, and that's going to be our data transmission rate. And that's basically it. So of course, we have a status register, which is when we're trying to see whether or not it's done transmitting. So we have a SPSR. So if you see up here, we're looking to see if we have any data still in the buffer to be transmitted. So this is basically, we're just waiting for the data to be transmitted while we're in this loop. So anyway, I mean, that's basically it. So if we wanted to fire this guy up, and this is real quick and dirty. This is one of those 10-minute programs. So we set up our various. I'm only doing the reference divider. So the reference divider here, and so we're doing in this, we're doing like this bit, a few of the other bits. Let's see. Nope, not programmable divider. My bad. We're doing this bit, this bit, this bit, and this bit. So you see, we got 2, 3, 6, and 7. 2, 3, 6, 7. As 0001. So 0001. I know that this doesn't make a whole lot of sense with what's going on here, but those who know C will pretty much. I don't know how. Difficult to explain, and I really don't want to get into a C programming lesson, but it's basically what we're doing. We're just setting in various positions in this 32-bit integer. We're just setting various. We're just toggling some bits in there, and shifting the whole mess together. And then what I'm doing here is I'm converting them to essentially so that I could do array, and I can fire off 3 sets of 3 bytes, to make the 24 bits. And that's basically it. So if we look at what this generates, if you can remember, our initialization string from the previous video was for our divider was 00088 and 80. If we just make sure that this program is uploaded, so this is a whole whopping 260 byte program. You see it down here in the corner. It goes so fast because it's so small. We just run this guy, and see we got some delays in here. So delay 2 microseconds where we set the slave select. Transmit the data, delay for 2 microseconds again, and it's just delay 50 milliseconds. Just basically go around and around and around. So we're just going to transmit the reference divider data over and over and over every 50 milliseconds. So we run this and see that it's pretty much just transmitted every 50 milliseconds, give or take, over and over and over again. So if we look at that data, this is only one packet that we're transmitting. See, this data is just perfectly clean. So now we just look at some timings, which is what the previous microcontroller, the one in the radios, since it's bit banged, you see various timing problems. One of the timing problems you see is with relation to the clock pulse and data pulses. So if you look at these, you see that these clock and data pulses are happening at the exact same time. And on the other one, they were not. So you can see that we've got nice clean transitions in here with our data pulse and our clock. So the transitions are essentially perfect. We don't have any odd problems with the decoder. None of that, and all this is the same. And of course, most importantly, if you remember, our initialization that we have to transmit is 000880, or our reference for our reference oscillator reference divider that the radio is transmitting, it's 000880. So it's just, bang on. And our slave select is not riding so close to our clock pulse, because the other one was like right at like 2 milliseconds, and it needed to be probably greater than 2 milliseconds, because the data sheet here specifies that that these things need to happen. When we've got our chip enable, you see we've got this TDP value. It's greater than or equal to 2 microseconds, and so I've delayed by like 2 microseconds, and since this portion is bit banged, it's going to be a longer delay than that. It's probably going to be closer to 4. So let's just see what it is. 3.8, it's about right. I figured it was going to be close to 4. So there's more time here for things to happen. Now we want things to happen quickly, but we're not going to notice a few microseconds, but this chip will. So if you can loosen things up a little bit. I suspect that this just the reason that they had those things so close together is just sloppy coding in the microcontroller. But you can see this is just as clean as can be, which is exactly why, if you can use the hardware SPI, if your chip has it, you're probably better off using it. So anyway, there's the code if you really want it. It's basically the same thing to send the actual divider data. So and this is, like I said, this is a quick and dirty. This is obviously the other code I have is somewhat better than this, but needless to say, this should work just fine. To expand off of, maybe not stuff your bits and some pointers that you can then point to, and then send them individually. I'm sure you can put that in a loop and maybe be a little bit more elaborate, but since we're essentially sending fixed length data, this is probably just fine anyway. Because we're just sending. And you have to keep in mind, we have to send it this way, because this register will only take 8 bits. So actually, let's just show what's going on there. We just look at our I/O there, and we just look for the SPI registers, and we just look for SPDR. You see, there's nothing in it right now. So if we go ahead and step through this, because remember, we don't have any data in there. So if we go ahead and step through this, again, there's no data in it. Actually, the reason there's no data in it is because it's actually already been cleared, because the breakpoint moved on me. Yeah, the breakpoint already moved on me. Of course, that's why there's no data in it, because it's just as soon as it's just flushed out that quickly. So yeah, not a good example, but you'd see. Another good thing about using the Atmel Studio debugger is you have all these wonderful things that you can tinker around with. So anyway, that's basically it. So I hope that was informative, interesting, so on and so forth. Questions, do ask, but if I don't get back to you quickly, because it's 1 in the morning now, and we're leaving for the coast, and probably I don't know. I think we're gonna leave at like maybe 9-10 in the morning. So I better scurry on off and stop playing around with this, and move on with life, as they say. So hope you guys found that interesting, and see you guys when I get back from holiday.